Hello everyone, welcome to In 5 Minutes. In this video clip, we will discuss the second type of practical sampling, which is called flat top sampling. Now, the name itself is self-explanatory. In the previous case, we had seen natural sampling, in which we multiply the modulating signal with train of rectangular pulses, and the amplitude of every pulse gets changed according to the original amplitude of modulating signal. Now, this is something does not happen in flat top sampling. In flat top sampling, the amplitude of pulse will definitely change, but it will take only the starting amplitude of the original modulating signal. You can see the first rectangular pulse amplitude is increased to the initial amplitude of the modulating signal, and thereafter the pulse magnitude is not changed, it is constant. Similarly, when the second rectangular pulse arrived, its amplitude is increased to that current value of the modulating signal, and thereafter again the amplitude of the pulse remains constant. So as you can see, in case of flat top sampling, we will change the amplitude of the rectangular pulses to the amplitude of modulating signal, but that is done only for the initial amplitude. Thereafter the rectangular pulse is kept constant. So this is called flat top sampling. As you can see, the top of every rectangular pulse is flat, it is constant in nature. So this is how the flat top sampling is obtained. Now let us do the small mathematical analysis. We will later on try to compare flat top sampling with the natural sampling. So how can I define flat top sampling? There is one very simple way in which we can define the flat top sampling. Let us assume that there is no rectangular pulse available. If it was an ideal sampling process, then instead of every rectangular pulse, we would have taken an impulse function, an ideal impulse function with zero width and infinite magnitude. In that case, we multiply the impulse with the modulating signal m of t. We adjust the height of the impulse according to the magnitude of the modulating signal. That doesn't mean the magnitude of impulse function gets changed. It is always infinity. We simply change the area under impulse function. In simple words, every impulse function that we have is associated with some scaling factor. So when we multiply the impulse function with modulating signal, we simply change its scaling factor. So we are first considering the ideal sampling, for which we have already done the mathematical analysis. We are considering some system with transfer function h of omega. This is frequency spectrum of the system, or I can also call it h of f. Omega will be in radians per second, f will be in hertz. And if I'm defining this system in such a way that when input to this system is ideally sampled signal, the output of the system should be practically sampled signal. That means a rectangular pulse with the width equal to tau and height. This time it will be the height or the magnitude which will define the value of the original modulating signal, and that will be equal to A. To be precise, let us define this rectangular pulse to be starting from 0 and extending up to tau, so that the width becomes tau and its magnitude is equal to A. So I repeat, the representation of flat top sampling that we have taken is something in which we have some system which we are yet to define. On the input of the system, we are applying ideally sampled signal. Right now we have considered single impulse function with scaling factor A, and output of this filter should be practically sampled signal, to be precise flat top sampled signal with the rectangular pulse with amplitude A and width equal to tau. My aim is to find the frequency spectrum of flat top sampled signal. We every time find the frequency spectrum. We found the frequency spectrum of naturally sampled signal also. We had found initially the frequency spectrum of ideally sampled signal. Now my aim is to find frequency spectrum of flat top sampled signal. Frequency spectrum help us to understand the effect of sampling process in the frequency domain of the signal. To find the frequency spectrum of the output signal, let us find the frequency spectrum of the input, which is ideally sampled signal, and let us try to define the frequency spectrum h of omega or h of f of this particular system that we have.